Hello, my name is John Ferry. I'm a student associate here with the Displacement Sensors team at Lower Sensei Microstrain. I'm going to walk you through a quick start guide for how to set up the DMOD digital. First, we will be connecting our Microstrain LVDT sensor, pictured there, to the cable with a LEMO connector. We will then screw this sensor cable into the DMOD digital via the M8 port in the front. Just line up those 4 pins and then screw it in. Next is a 12-volt DC power supply, which will be connected to the back of the DMOD using a barrel jack. Now this signal conditioner has 2 ways to measure the output, digital and analog. We will be connecting the micro DB9 serial cable, which can operate RS-232 or 485 interface. I have this connected to a USB adapter so that I can use my laptop. Next, we will connect the mini BNC analog jack to the DMOD digital, while the other end will connect to a data acquisition device. I'm doing this with a pair of flying leads. After making all connections, our engineers recommend waiting 10 minutes before taking your first measurement. I will now be showing you how to connect the DMOD digital device to Sensor Connect. First, I am opening Device Manager to see that the DMOD is connected to serial port COM9. Then I will be adding a new device, selecting serial, importing COM9, and keeping the standard baud rate of 115,200. Now I will resume data collection and move over to the Data tab, where I have a numeric display and time series widget, allowing you to see the change in measurement as I actuate the sensor. And there you go. You can see there's a sensor output here in millimeters on the Sensor Connect screen, and in volts here on the digital multimeter. I'm going to set this sensor to 3 specific lengths, 1, 2, 3, then do a short screen capture to demonstrate how we use these analog voltage values. In this table, you can see the 3 measurements I took and their corresponding analog output voltages. One at an arbitrary length of -57 millimeters, one almost fully retracted at a length of -70 millimeters, and one near the mid-stroke point of the sensor at just about 1 millimeter. To do this conversion, I will be using a Python notebook through SensorCloud's math engine and just running a very quick script I wrote. In this first cell, I am initializing all of the calibration data, which can be found on the certificate of calibration. No sensor and signal conditioner pair is shipped from our facility in Vermont without one of these certificates. You can see here that the linear slope is almost 15 millimeters per volt, while the offset is about -79 millimeters, which I entered into Python right here. While the DMOD digital's accuracy comes from the digital filtering and internal lookup tables, the signal is converted into an analog voltage for those customers who have an analog system in place. Therefore, we will only need to use the linear fit to convert these values back to displacement in millimeters. For other signal conditioners, the multi-segment or polynomial fits would produce better accuracy. As you can see, I entered the analog output voltages here in Math Engine. Now as I run these cells and apply the linear fit, you can see just how accurate the analog voltage value is. Let me just enlarge this for you. Now you can see there's only about 0.1 millimeters difference from the digital, and this is on a 150 millimeter stroke sensor. If you follow this link to our website, we will have additional support materials to answer any further questions.